The next biggest type of numbers are the rational numbers. The symbol for rational numbers is the bolded letter Q, which can be represented by just drawing a line on the opposite side of the Q. Some examples of rational numbers are -1/2, 2/3, -5.44444. The line over the 4 means the 4 repeats. 0.37, 9, and we could keep going on with different examples. A rational number looks like a over b, where a and b are integers. So it's any fraction, any number that can be represented as a fraction. The one thing that you should remember though is that b can never be 0. We can never have 0 on the bottom of a fraction. So rationals are any number that can be represented as a fraction, a over b, where a and b are any regular numbers, positive or negative. Well, a student definition is to remember that word fraction for rational numbers. Any number that is a fraction or that can be made into a fraction is a rational number. The mathematical definition is exactly like the representation I have here. A over b, where a and b are integers and b is not 0. Some helpful insights to remember rational numbers is rational numbers is represented by the letter Q, and Q stands for quotient. Well, fractions are just division problems. So the answer to a division problem is called quotient, which is the same thing as the initial Q. Q stands for quotient. Rational numbers include integers, decimals that stop or repeat, and fractions. And any of these can be positive or negative. What does the number line look like for rational numbers? Well, we don't know that. We can't draw it because there's still spaces in between these numbers, and all these fractions add up to a lot, so we don't know what the number line looks like. But the rational numbers are countable. How do we count the rational numbers if we can't draw it on a number line? We use a grid. We use a grid of rows and columns. The rows stay the same as 1s, 2s, 3s, 4s, 5s, and the columns stay the same as 1s, 2s, 3s, 4s, 5s, and they continue on that pattern forever. This counts all the fractions that are possible because this takes care of every possible fraction there is, since these go on forever. To count these, all we do is we cross out anytime we have repeats. We have a repeat here of 2 over 2, which is the same thing as 1. Cross that one out. 3 over 3 is a repeat. We cross that one out. 4 over 4, a repeat. All these are 1, which is already taken. 1/2 is the same thing as 2 over 4. We cross that out. And what we would do to count these is we would cross out all the repeats and then count in a zigzag motion. So we start here at 1 over 1 and go to 1 over 2, 2 over 1, 3 over 1, skip this one, 1 over 3, 1 over 4, 2 over 3, 3 over 2, 4 over 1, and we would zigzag all the way through counting these. First one, second one, third one, fourth one, fifth one, sixth one, and this is a way that we can count and show that the rational numbers are countable. The next type of number set are the irrational numbers. The irrational numbers are represented by the bolded letter I. Irrational numbers are numbers that when we see them, we see them as a decimal, and the decimal never ends and never has any repeating pattern. This would be an example of like the square root of 2. What number times itself is 2? Well, 1.4142 keeps going on forever, varying, times itself is 2. So an easier way of representing irrational numbers are its simplified form as a radical 2. So we would represent it as radical 2 instead of 1.4142, etc. Same thing, it can be also negative with a square root of 5. There's no number times itself that's 5. What number times itself is 5? 2.2360 blah blah blah. We don't know that. It goes so far and it continues on forever. So this number is negative, meaning this number times itself has a negative in front of it. There's also cube roots. What number times itself 3 times is 6. 1.81712 going on forever times itself 3 times is 6. This number is irrational because it's a decimal that does not end. There are also a few famous irrational numbers like the number pi. The pi is 3.1415, and to be smart and to impress your math teacher, try to memorize pi as far as you can. There's also a world record for how long you could memorize pi. How many digits can you memorize pi for? There's another number called e that's also very important in math. That's 2.7182, and this number varies going on forever. To help students remember, it's any number that cannot be expressed as a fraction, or that cannot be expressed as a over b, where a and b are integers and b is not 0. But the easiest way to remember it is any number that cannot be made into a fraction. Well, how are we going to help us to remember it? Well, the mathematical definition is any number that's not rational. But to help us remember it, we see the word ir, or the prefix ir, in front of rational. Ir is a prefix that means not. So the word itself is irrational or not rational. So irrational means not rational. How would we represent this as a number line? We don't know how to represent this as a number line because there's spaces in between where all the rationals are. And there are so many irrational numbers that they cannot be counted in any order. This is our first number group that cannot be counted. It's bigger than all the rest. This is our first one that cannot be counted, irrational numbers. The next type of numbers are the real numbers, represented by the letter R that's been bolded. The real numbers can be any of the numbers we've discussed so far: -5, 0, 2, radical 7, the fourth root of 10, pi, -e, 5/9, any decimal, repeating or non-repeating decimal. Its general form is the letter A. This is our normal variable that we would use. Any letter can be represented to represent a real number. A can be any rational or irrational number. An easier way for us to remember it is it's any single part number, or a decimal, or a fraction, or any number that cannot be made into a fraction. So it's basically all the numbers we've discussed so far. A rational or irrational number is its mathematical definition, and a real number can be any of the numbers that we've gone over. We can draw the graph of a number line, which is a number line that's been completely shaded in. There are so many real numbers that there is no way of ordering it to count them. The real numbers are uncountable.